In our last video, we were talking about how the equilibrium constant is very useful in helping predict the concentrations of reactants and products once a chemical reaction has reached a sort of stasis at a particular set of conditions. The acid dissociation constant, which we'll be exploring in our next unit, is a form of a KEQ that is used to predict the results of acid-base reactions, and in particular, what will happen when a particular acidic compound is dissolved into an aqueous solution. This is really useful when we were dealing with what are called weak acids. Most acids are not like hydrochloric acid or sulfuric acid. In those cases, hydrochloric acid, we can predict, will basically generate an acid molecule for every HCl that goes into an aqueous solution. This is not the case for the vast majority of acids. Most of them will only generate a few molecules of H's, so to speak, in aqueous solution per mole. Some acids that are weak are stronger than others, but generally, if it is not a strong acid, it has a KEQ of less than 1. Now, of course, most of our acids that are well known to chemistry have been evaluated through constant experimentation and have been assigned a particular KEQ, or what would be called a Ka, an acid dissociation constant. In the case of acetic acid, its KEQ, or Ka more specifically, is 1.8 times 10 to the negative 5th power, making this clearly a weak acid. Acetic acid is better known to us in a dilute form as vinegar, but in concentrated form it is quite powerful and definitely something that should be dealt with under the fume hood. I have here some glacial acetic acid that's gotten pretty old. There's not a whole lot left of it, but I assume it's been taken well care of, and it's more or less in the same concentration that it was when it was new, and I would say it's been some decades since this actually was bought. Glacial acetic acid is unusually pure, about 99%, and so that translates into about a 17.4 molar concentration. Let's say that I wanted to have a more dilute form to work with, say a 1.2 molar concentration. Well, what would that look like? First of all, we would want to know how to produce that in a dilution from its original high concentration strength. That's where we bring out the old M1V1 equals M2V2 formula that's on everybody's reference sheet to help us formula out how to dilute something properly. Let's say that I only want 50 milliliters of a 1.2 molar solution. So in other words, we would want to know how many milliliters of our concentrate would we put in and then bring to the 50 milliliter level with distilled or deionized water. This equation produces 3.44 milliliters that would go into 50 milliliter solution. And that's what I've done here with this. Now, of course, we're not going to get total perfection here. There's limitations of my pipettes, my own steadiness of my hand, and who knows whether or not that this acid has not undergone some sort of dissociation already. Some acids have better shelf lives than others. We're going to find out how good this one is. So one way of evaluating perhaps how good a shape this acid's still in is predict what kind of pH that it would have and then test it. If it's fairly close, we can assume that this acid is still pretty good. Now, one thing to do remind you that when we were working with weak acids and bases, it's true that we may have the benefit of a Ka or a Kb for bases, but that is pretty much a pooled in value basis on hundreds of experiments. There's going to be a little bit of variations. The purity of your water that you're diluting things in may vary. Your own measuring equipment isn't going to be perfect. So a lot of times when we're dealing with weak acids and constants, getting a result that's within an order of magnitude of the expected result is pretty good. no point in beating yourself up if you don't get exactly the pH in this probe that we hope that we're going to get. But I think that we can get fairly close, assuming that this acid is still pretty much in the condition it was when we bought it or our predecessors bought it. So how are we going to go about that? So what we do here is we're going to plug in our KEQ and use an ice chart to generate an algebraic expression that can help us predict what are going to be the concentrations of our reactants and our two products when we are finally at the end, or on the E, better known as equilibrium. So let's take a look at the acid that we're working with, the acetic acid. It, of course, is a hydrogen ion and an acetate group. This is, of course, a polyatomic, which has a -1 charge. And like all polyatomics, it's a covalent compound, and almost all of our well-known polyatomics are negative, with exception of the ammonium. So what will happen is when I diluted this almost 99% pure glacial acetic acid in water and it dissolved into solution, certainly some of our acid molecules were formed in water, or more generally what they would call a hydronium, H3O positive ion. Either one's essentially the same thing. I'm just using H plus for illustration. And then we would presume an equal amount of our acetate ions. So how much is going to actually form? So we walk through the ice flow here. So we have our initial concentrations of 1.2 molar concentration of acetic acid. And as in the cases of all of other problems we've been working with on ice charts, we start off with concentrations of 0 for our products. Then we undergo the C, the change. We assume that we have an X amount of this initial concentration that's going to be lost. And because we've got kind of a 1-1-1 stoichiometry here, we can assume that an equivalent amount will be gained by the hydrogen molecules and our acetate molecules. Then we come to our equilibrium, which is expressed as our initial concentration minus what was dissociated, and then for our products, the amount that was gained. So this is a little bit simpler. We have no additional coefficients to work with here. So now we take our KEQ formula, KEQ equaling products over reactants, and we start plugging in our expressions. Our KEQ, as we looked up in the book, or I looked up in the book this morning, is 1.8 times 10 to the -5th power. We're assuming that we're going to produce two X's, our hydrogen ions and our acetate ions. So we'll take those two X's and make them X squared for simplicity. Then over here on the reactant part of our expression, we've established 1.2 minus X, representing the molar concentration we started with and the amount that we assume stoichiometrically is going to be lost. Once we start rearranging this, we start having a more familiar algebraic expression. And then we can rearrange this into quadratic and setting everything to 0, which I just forgot to do here. And so we wind up with a quadratic equation which rearranges this to 1x squared plus 1.8 times 10 to the -5th power x minus 2.7 times 10 to the -5th power. So we now have our coefficients that we can use for our quadratic equation. Once we've found our appropriate answer, we've solved for x, and we can plug these in here. So A is 1, and that'll go here and here. B is 1.8 e -5. Those will go into these two places. And then C, 2.7 times 10 to the -5 will go right here. As we all know, with quadratics, it generates two potential answers. One answer based on adding this square rooted expression, and then another answer based on subtracting it. So we get our two potential answers. And answer 1 does not work, because what it does here, if we put it up here, it yields a negative concentration. We can't have a negative concentration of anything. It's just illogical. So by default, we have answer 2, which is 5.9 times 10 to the negative third power. So now we can evaluate X and put it into our final end states here, our E's, our equilibriums. So for the acetic acid, we have 1.2 minus X. That turns into 1.2 minus 5.19 times 10 to the negative third power, and then you would evaluate that. But we're mostly interested in how many acid molecules are going to be generated. The acid molecules and the acetate molecules will be the same, and which is, of course, 5.19 times 10 to the negative third, because that's your X. So finally, what pH do we predict this solution is going to be? We take the negative log of the molar concentration of our predicted final endpoint concentration of hydrogen ions, and we have a predicted pH of 2.28. So then we can see how well it holds up. We use our handy little probe here, and I actually did this a few minutes ago. I let it sit for about our good 25-30 seconds, and I got a pH that I think was pretty close, about 2.44, which is not bad. And remember, there's going to be some deviations from the predicted, such as, you know, the accuracy of the calibration of this instrument, which I think is pretty well calibrated, the accuracy in me drawing out our concentrate and adding it into the solution of water, the cleanliness of the glassware, any residual ions that may be in this distilled water, and many other factors. But still, I would say that's pretty close, and that would tell me that this glacial acetic acid is still in pretty good shape and still servable for general chemistry use. So in conclusion, the acid dissociation constant, often denoted as Ka, is just a special case of KEQ to give us a sense of what can we predict when we dissolve acid-generating molecules into aqueous solutions. In the case of glacial acetic acid, which is a weak acid, we know that we're not going to be producing the exact stoichiometric amount of acids to molar concentrations of glacial of the acetic acid itself. So, using a dissociation constant in the ice chart, we can figure out how much actually will be generated when we dissolve this concentrate into a more dilute solution of water.